This lecture. This is a continuation of my previous lecture where we solved a problem on first order system dynamics. So this is a continuation of the problem. In the previous class, which was titled as PC43, and we had solved part A and B, part A and part B. Part A and part B were, and this is a problem taken from the textbook Process System Analysis and Control by Kaufman DR. So in that previous lecture titled as PC43, the link is available below as well as above. We had found out the difference between the indicated temperature and bath temperature at 0.1 minute and 1 minute after the temperature begins. We had first found an expression for the difference between the indicated temperature and the bath temperature. It is in our notation x minus y, and found the value of this, determine the values of this error x minus y at 0.1 minute as well as 1 minute. This was done in PC43, and this class is a continuation of this PC43. So where we are going to solve part C and part D. So before I go into that, I would like to request you to kindly subscribe to this channel. Please subscribe to this channel and share to your friends. If you have any comments, please leave the comments on the section below, comment section below. And more importantly, please visit the channel page and hit the subscribe button. So that will help you to be notified of my upcoming video lectures. Well, now we'll go into the remaining two parts, part C and part D. Now the next question. What is the maximum deviation between the indicated and bath temperatures, and when does it occur? The maximum deviation between the indicated temperature and bath temperature. That is, this is the difference between indicated and bath temperature. When it will be maximum? When it is going to be maximum, and what is the maximum value? So what is the maximum value of this? If you see this bracketed term here is a fraction, 1 minus e power, because e power minus exponential negative number is also a fraction. So, and this 1 minus fraction will be a fraction. So maximum for x minus y to be maximum, this term has to be maximum. This bracketed term must be maximum. That bracketed term will be maximum when maximum value of bracketed term is what? 1, because it's a fraction. And that will happen when this term is 0. When it will be this term 0? When t equal to infinity. So this error will become maximum when t equal to infinity. The error will be maximum when t equal to infinity ultimately, after a long time. So C part, maximum error happens at t equal to infinity, as t tends to infinity. So x minus y max is going to be how much? Simply m tau. M is how much? Rate of change 1, tau is 0.2. So 1 into 0.2, 0.2 degrees. So there will be a permanent error of 0.2 degrees even after a long time. So after the ultimate value is reached, when the final steady state is reached, still there will be a difference of 0.2 degrees between the x and y, between the true value of the bath and the indicated value of by the thermometer. So this maximum error has a name, and it is known as dynamic error. It is known as dynamic error. So this difference between the indicated and the bath temperature, the maximum value of this error, which happens at infinite time, is also known as dynamic error. So this is known as dynamic error. This maximum error is known as dynamic error. So, and what is the value of this? X minus y. And for a first order system where k is 1, this dynamic error will be m into tau. Dynamic value of dynamic error is going to be m into tau is a dynamic error of first order system with the gain 1. So what is dynamic error? It is the difference between the true value of the measured variable, difference between the true value of the measured variable, which is x, and the value indicated by the measuring instrument, which is y, under varying conditions. Under varying conditions, that is important. Under varying conditions. So that is known as dynamic error. How do you explain dynamic error? Dynamic error is the difference between the true value of the measured variable and the value indicated by the measuring instrument under varying conditions, under dynamic conditions. So that is important. So that is dynamic error. If the conditions are not varying, if there is no change in the surroundings, still if there is a difference between the indicated value and the true value, suppose there is no change in the bath temperature, constant, and thermometer does not show the bath temperature exactly. If there is a difference between that bath temperature and the indicated temperature, when there is no change under static conditions, if there is a change, that is known as static error. That is known as static error. So in this analysis, you have been seeing the dynamic analysis. So in all this dynamic analysis in this class and previous classes, we assume that there is no static error. That's why initially we have taken x is equal to ys. At steady state conditions, when there is no variation in the surroundings, x's and y's are equal. The indicated temperature and the surrounding temperature, true value, are equal. That means there's no static error. So this dynamic error definition is under the assumption that there is no static error. Well, now there is another part. Plot the forcing function and the response on the same graph. After a long enough time, by how many minutes does the response lag the input? So you have to plot x of t, this equation. You have to plot x of t, this equation, by assuming various values of t. Anyway, it's a straight line. Only one value is enough, and 0. It passes through 0. Take one value and you can draw a straight line, mt. And then y. Y is this is equation for y, right? Yes, this is the equation for y. You can take k is 1. K is 1, we have taken k is 1. K is 1 for thermometer, right? K is 1 for thermometer. And plot this y. Both plot x and y on the same graph. What will be the nature of y? So this is not going to be a straight line. So this will be a straight line after some time when for long values of t, for large values of t, this term becomes, for large values of t, this term becomes 0. So you are going to get, you will get, if this term will be going, if this term will be, the effect of this term will be nil for large values of t. So you will be having only this t minus tau. So t minus tau is an equation of a straight line. So you will find when you plot this, initially it will be a curve because of the effect of this term. And after a long enough time, this term becomes negligible, so you'll get a straight line. So it will look like this. We plot x and y on the same graph. From those equations, make an actual plot by taking different values of t and calculating y by the response equation. Response equation is this. Response equation is this. You will get these two graphs. As I said, the response will be initially curved, and after a long time, after some long time, when this exponential term becomes very small, it will become almost linear. Now this question is after long enough time. Last part of the question is after long enough time, by how many minutes does the input lag the response? By how many minutes? So take a region where these two lines are almost parallel and find out by how many minutes does the response lags. This is a horizontal distance. The horizontal distance between the two curves after long enough time will give you what is the lag between the input and response, right? That is somewhere here you draw a horizontal and find out. You draw a horizontal here and find out what is the time lag between here, between this and this. What is the time lag between the input and response to read the same value. Horizontal means y-axis same. To read the value, to show the same value, how many minutes does the response take more than the input? So by how many minutes does the response lag the input? You can find by this horizontal value somewhere here. So you can find the value and please report it in the comment section, your answer. Please report your answer in the comment section below. And this graph will also show what is the dynamic error, the difference between the indicated temperature and bath temperature. That is, if you take in the long and after long enough time, you find out what is the vertical distance. What is the vertical distance? Somewhere here. Read the value on the y-axis. Read the value on the y-axis. This value how much on the y-axis? That will be the dynamic error. So if I plotted correctly, you will get this value as how much? How much dynamic error you got? This vertical distance represents the dynamic error, the difference between x and y. And if I plot it correctly, this will give you, this will the reading, this vertical reading will be the dynamic error, which will be equal to how much? 0.2 degrees. Well, try to, when you draw these graphs as per the actual values, you can get these answers. Well, I hope you have understood this response of this first order system for a linear input. How does it respond for this linear input? We'll see with more examples in the next classes. See you.